Good afternoon. Thank you for joining. It's a pleasure to see many familiar faces. We're starting a session, I forgot the number already, 2.something, 2.6. It's active flow control. I have interesting speakers. And I'm going to start with Dr. Martiqua Post. She's a professor at the Air Force Academy. And she's currently a deputy manager at DARPA, working on the X-65 project, and is going to inform us here of where they are. Thank you.
All right, good afternoon. As Paul mentioned, well, he's the session chair. I'm also the other session chair. But my name is Martiqua Post, and I'm from DARPA, which is the Defense Advanced Research Projects Agency. I'm from the Tactical Technology Office, also known as TTO. And today I'd like to talk with you about the X-65, which is the CRANE program. You can see that CRANE stands for Control of Revolutionary Aircraft with Novel Effectors. In this program, we're developing, building, and flying a unique vehicle that will demonstrate active flow control technology. This full-scale experimental aircraft has been officially designated as the X-65. Oops. All right, so experimental aircraft are used to test new designs and technologies and are at the forefront of technology and research and development. An official X designation is given to an experimental aircraft as part of the United States Military Aircraft Classification System. The X, of course, stands for experimental, and these were started back in actually 1947, where the X-1 demonstrated that we could fly faster than the speed of sound. And these used just air because wind tunnels couldn't match the flight conditions for that. And so DARPA X-planes are proof of concepts and tech demonstrators. You can see that we've been developing different aircraft on kind of a 2 to 4 year cadence. And they are tech demonstrators at a convincing scale. They're not prototypes, so we're not anticipating, building production aircraft that we test. They're just experimental planes. And some of the planes at DARPA are official X-planes, but some also don't have X designation. Other X-planes you can see on there, 1990, X-31, which is the Canard Delta Wing, which tested thrust vectoring. You can see in 2002 the X-45, which was the unmanned combat vehicle, next generation of autonomous military aircraft. And you can see the X-51, which is an unmanned hypersonic vehicle. And to the far right, in 2025, which is next year, is the CRANE vehicle, which is the X-65. So DARPA builds these as part of a high-risk, high-reward tech development. And again, the CRANE program is demonstrating active flow control technology. The original CRANE program was, the vision was to design, build, and flight test an X-plane that incorporates active flow control as the primary design consideration. So many of you who've worked in the area of flow control know that flow control is often used as an add-on, as an after the fact to try to fix an aerodynamic problem. This program tried to incorporate flow control at the beginning as part of initial design consideration. There's really 3 pillars to the program. The first is the compelling capabilities. And so by flying an X-plane, we look to demonstrate quantifiable benefits that will bring active flow control to airplanes. Next, we want to mature technology. We believe that active flow control has been matured. In fact, 25 years ago when I was a grad student, I was working in the field of active flow control, and DARPA funded my work. So 25 years later, as we've developed flow control technology, it's great to be part of a program that my PhD actually helped develop. So now we have mature enough technology, and we're going to demonstrate that with, and hopefully it'll be reliable. And as part of phase 0 of this program, we developed different design tools as well. And finally, we want to demonstrate this technology in a real and relevant environment. So this means scaling appropriately and demonstrating system performance. One program goal was to really leverage the benefits of active flow control, again, by incorporating them early in the design process. So throughout the past quarter of a century, the term active flow control has been used quite frequently, and it includes a wide range of fluid dynamic control approaches. So broadly defined for the Crane program, flow control is a mechanism that alters the aerodynamic flow field through mechanical actuators or fluid actuators or plasma actuators. And so we can change the flow of fluid on the surface or at any of the aerodynamic interfaces, such as the wing fuselage inlet or the nozzle. You can see several different methods for flow control there listed on the slide. And active flow control can affect the flow in many ways. We can alter the boundary layer, we can alter the boundary conditions, we can introduce the vorticity into the flow, energizing the flow, or we could increase circulation. And we can also apply active flow control to steady and unsteady flow conditions. Crane uses the Coanda effect, and we use steady blowing in this case. The upper left-hand picture shows that in 1903, aircraft have been using movable control surfaces to control an aircraft's flight. So of course the Wright brothers used wing warping, and to actually circumvent the patents that the Wright brothers had on that, hinge surfaces were later designed and used. One additional benefit for using hinged surfaces was that hinged control surfaces alleviated some of the structural stresses and the manufacturing challenges that were associated with just kind of wing warping. As was mentioned, active flow control manages, amplifies, disrupts, and affects the flow around the vehicle. So flow control can be incorporated into any vehicle air platform to tailor the airflow around the vehicle, and these forces can be used to control the vehicle or steer the vehicle in a desired manner. So the X-65 vehicle will demonstrate safe control and maneuverability at a relevant scale without the use of conventional hinge control surfaces. So we won't use conventional ailerons, elevators, or rudders, like we've been flying planes for the last 100+ years. So this is actually quite revolutionary. Integration of the flow control onto the vehicle and into the flight control system really represents a paradigm shift with respect to vehicle design and operability. The image there on the right shows different types of active flow control concepts that have been explored within a NATO task force. Philosophically, we have three primary lanes of thought. The first one is as active flow control as the primary design consideration. So a goal of the Crane program was to inject disruptive technology into the aircraft design process, shifting the aircraft design methodology moving forward by maturing flow control technologies and design tools to a level that allows them to be incorporated early in the design process, and also with a confidence level that optimizes the full utilization of their benefits. In other words, the program should support the development of conceptual design tools and mature required technology to the point where active flow control could be incorporated in future vehicles from day one, not as an add-on as we normally do with flow control. The second would be affordable approaches. So to reduce the program risk outside of the unique configurations, Crane performers, and initially in phase 0 we had 4 performers. The performers were advised to maximize the use of commercial off-the-shelf parts and components for non-flight control subsystems. And the Crane program also excluded already proven technologies such as thrust vectoring and other traditional moving parts. We wanted to design safety in from the ground up, And so we're doing airworthiness, and we're actually using the military approach, so Mill Handbook 516, which is quite extensive, and they will help us to get our flight release. And then finally, a compelling demonstration. Again, we want to demonstrate this at a relevant scale. So the vehicle had to have a gross takeoff weight. You can see it here on the right-hand picture, between 1,000 and 20,000 pounds on the y-axis, and we wanted to have it fly within Mach 0.2 and 0.9, which is there on the x-axis. And the vehicle should have the active flow control system integrated with the vehicle flight control system, and it had to be within budget and within schedule, within the DARPA timeline, and notionally within a 5-year program. In addition, these discrete requirements, DARPA expressed a desire to have this vehicle have residual test utility beyond the base test that we're planning on doing next year. And so the actual vehicle that we're building has been designed kind of in that dark blue box that's over the teal box in this figure. The program has, I guess, 4 phases. This one outlines phase 0 and phase 1. So initially we had 4 performers. You can see there, Aurora Flight Sciences, Lockheed Martin, Georgia Tech Research Corporation, and BAE Systems. And so phase 0 here was our conceptual design phase, getting the aircraft design right and deciding what we wanted to go and build. And then the program had, so it had 4 12-month phase 0 efforts, which then culminated into a conceptual design review. And at the end of that, 2 performers, which were Aurora Flight Sciences and Lockheed Martin, matured their designs a little bit further through preliminary design. Phases 2 and 3 are not shown here, but I have them on a later slide. So in phases 0 and 1, which actually predates my time on the program, again, was for conceptual design. And we had a number of partners. You can see the number of partners across the top. So we've got the Air Force Research Lab, the Office of Naval Research, the Engineer Research and Development Center, NAWCAD, which is the Naval Air War Center for Aircraft Division, NASA, of course, the Army Research Lab, the Air Force Office of Scientific Research, and the Royal Air Force RCO, or the Rapid Capabilities Office. We all teamed together as part of this program. So phase 0 performer, actually all 4 of these are phase 0 performers, and the bottom 2 are the ones that did not go to phase 1. And the first one there is the Georgia Tech Research Corporation. They explored a channel wing design, and their decision to explore this design was primarily based on mission impact. So they saw and found a higher effectiveness of active flow control technologies at lower dynamic pressures. BAE Systems also focused on extracting the greatest control effectiveness from the smallest footprint design, which led them to implement supercritical circulation control, also utilizing the Coanda effect, and they did this on a delta wing platform. And then our phase 1 performers, which on the right side was Lockheed Martin, they explored a variety of platforms with blowing and fluidic fences and spoilers, but in the end they tested a subscale vehicle that you can see here, which contained a quarter-size jet engine with an integrated active flow control system that used engine bleed. And then finally, Aurora, on the upper left-hand corner, developed a coplanar join wing. You can see it's a very unique-looking vehicle, and it has 14 conventional control surfaces and 14 active flow control effectors. Spoiler alert, that's the one that went on to phase 2 and 3. All right, so a little bit more about phases 0 and 1. I think, in my opinion, 2 advances, other than active flow control advances, that occurred in the last 25 years really enabled this program to become a reality. And one of those is computational fluid dynamics. And so this allows us to rapidly explore a larger design space, but also manage the complexity of the system that we ended up going with. And the second advance will be revealed later. So, integrating active flow control early in the conceptual design process, of course, required extensive modeling and testing of the component and subcomponent technologies to ensure that the system-level impacts were accurately quantified and the resulting unique aircraft configurations were valid and the designs closed. Key physics models were modified for active flow control, and of course, successful inclusion of active flow control utilized extensive multidisciplinary analysis and optimization activities. This is where some of our partners came in. To examine the trade space and select the design with the best vehicle level performance. And to accelerate the tool development and utilization, we had a couple different government agencies who provided high performance computing resources and numerical modeling expertise. Ultimately, as I mentioned before, Aurora Flight Sciences was down selected to then complete phases 2 and 3 of this program. So the preliminary design was refined and completed as part of phase 1. Phase 2 was for the detailed design and the critical design review, which was finished at the end of last calendar year. And now we're in phase 3, which is, of course, fabrication, integration of the subsystems, ground test, and flight test. So the program really started in COVID, and we ended phase 2 last year with CDR. And now we're in the fun part of the program where we're manufacturing, and then, of course, we will integrate and then do the ground tests early next year, and we will have our flight test probably around this time next year. This is a rendition of Aurora's concept for the X-65. Their conceptual design studies, of course, led to this selection of the code joiner wing. And you can see vehicle characteristics. It's a relevant scale vehicle, so it's about the size of a small business jet, about 7,000 pounds. It has four trapezoidal wing sections, and it uses active flow control, command effect blowing, and so the pitch effectors are in the inboard wings, so if you turn the front ones on, the nose goes up, and if you turn the back wing on, the nose goes down, and of course the roll effectors are on the outboard wings, which are modular. We can replace those with other flow control technologies should we use this vehicle later after this program. And then the yaw effectors are there on the vertical tail. So again, there's 28 effectors. 14 are conventional control surfaces. There's 7 on each side. So 2 on the front wing, 2 on the back wing, 2 on the outboard wing, and then 1 on the tail. And again, the wing itself is modular, so we can use it in the future to evaluate and test flight different flow control effectors. The aircraft, as it's shown here, is about 7,000 pounds, so it's similar to a small vision jet or business jet. The wingspan is 30 feet, so that's similar to an F-16, but I think really that's where the similarities end. The design is capable of Mach 0.65 at 20,000 feet. And it has a dedicated APU that supplies the air system blowing separate from the vehicle's engine, so we're not bleeding from the engine. It's the flow control system is a separate system under test. 4 different wing sweeps will allow us to pace our learning on how active flow control could be used during new aircraft design. This is just a cutaway of the vehicle. Here you can see the inlet. I guess the inlet to the engine. Back here is the engine. This is the inlet to the APU, and you can see kind of the air distribution system as it delivers air to each of the forward, aft, and outboard wings, as well as the vertical tail. The sizing of the active flow control system involved a wide design space and focused on things like the target flight conditions, the air source characteristics, the actuator selection, and we were able to optimize the air distribution system. As I mentioned before, besides active flow control being matured enough to build this vehicle, I felt like there was two other things that matured over the last 25 years. One of those being the computational fluid dynamic tools, and probably the other would be advances in additive manufacturing. And so these kind of advancements and for additive manufacturing really allowed us to generate some of these complex geometries within the effector banks and nozzles. Finally, here's one more cutaway of the vehicle showing some more of the subsystems. So the active flow control system is there in yellow, the propulsion system is blue, vehicle management system is in teal. One thing that we liked about this vehicle was it had a triply redundant flight control system, which gives us greater possibility and confidence that we'll have successful flights. And you can see fuel there in purple. The flight termination system is in pink, and the environmentally control system is in green. When we get to flight test, we will focus on 3 different objectives. The first of the flight test objectives will be calibrating the active flow control system against the conventional controls. So, for example, in this, a roll will be generated by deflecting the flap on an outboard wing section, and then active flow control will be deployed on the other side of the vehicle, and it will be used to null out the roll. The second phase will use active flow control as the primary flight control, and so basically we'll freeze the control surfaces and we'll maneuver only using active flow control. And then the final phase will be testing high lift. Currently, Aurora is fabricating the frame and the skins in their West Virginia office, as well as performing subsystem bench tests in their Virginia office. And we anticipate the structure will be ready for system integration by the end of this year. And so putting in the harnesses and getting things ready. And we look forward to the ground tests early next year, 2025. And of course, like the flight test in 1 year from probably about now. As mentioned previously, we anticipate vehicle utility after the program, so we are hoping that one of the other government agencies will adopt this vehicle and continue using it and testing other flow control technologies, and so we can use this to as a demonstration flight test bed. We'll continue to look for ways to transition the vehicle, and I think what's inspiring for me is really 3 different things. First is the next generation aircraft control capabilities that we could have. It could be totally different than what we have today with moving parts or wing warping or anything like that. Flow control enables the elimination of these moving parts. We could have quantifiable improvements in takeoff and landing performance, high lift, and maybe even enable airfoil agnostic enhancements. The second thing is, I think this vehicle also, and I think the excitement around this vehicle, also enables exploration of other advanced flow control technologies, and hopefully they will be able to exploit second-order effects and acting on flow instabilities to amplify the effect. And finally, I hope this will motivate exploration of other flow control technologies for totally different applications, not just these aero applications that I've identified here. So again, here's the vehicle. We have the opportunity to change the way we've flown for over 120 years. My partners here up on the table will be talking next in this section. So I'm joined by Fritz Langford from Aurora Flight Sciences, who's the chief engineer on the Aurora side for this vehicle, and Rene, I'm going to say Woszidlo, who's also been working on this vehicle. So thank you, gentlemen, for being here. Finally, I just wanted to put out a quick plug for DARPA. We're trying to discover new talent all the time and new opportunities for collaboration. So visit us at darpaconnect.us. We are providing networking opportunities, training and development, which could be in the virtual world or in workshops. And then if you would like more support, there's a customized support helping you put together proposals and answering, of course, the how Myra questions, which are DARPA standards. That concludes my presentation, and it looks like we got about 3 to 4 minutes for questions.
Any questions? There we go.
Thank you, Dr. Martiqua, for that wonderful presentation. My name is Benito Sebastian. I'm from BA Systems. I'd just like to ask a question regarding the control power effectiveness in adverse weather conditions. So, for example, if it rains, does the technology still work?
Would you like to take it, Fritz, or Rene?
That's a Rene.
Short answer is yes. I mean, water itself shouldn't matter. I mean, it may have an effect on the aerodynamic performance on just a baseline vehicle, but AFC itself should not change just because of rain. So maybe what you're also referring to, like turbulence level, like how much control authority do you get out of AFC? It depends. It's the usual answer. So depending on what, how your AFC system is laid out and what you're using it for, whether you have control surfaces deflected or not. So there's multiple variables there.
Just to kind of add on to that, so for example, have you considered in the design of the actual inlets, is there some mechanism to kind of prevent, well, I'm assuming it's not blowing all the time, you know, blowing out or blowing in. Well, I guess it's not blowing out all the time, so if it's not blowing out and if it rains, can water then get in? And is there a way to get rid of the water getting into the inlets or outlets?
I mean, yes, theoretically, there's certainly you know, an operational point around that. I don't think that was really a concern for this program, so I think we're planning on flight testing in good weather.
Yeah, so we're not planning on flight testing into the rain. But also, the air blowing system has a single inlet that's at the front of the vehicle, and I don't know if there's any drains attached in that area to, if it rains, for any of those liquids to come out. But the air does come in through a single inlet. It gets processed through the auxiliary power unit, APU, and then distributed through the system. There's also a heat exchanger in there, and probably a filter in there as well to keep other FOD ingestion from being a concern. I do know that also the GNC folks are looking at models of gusts and taking those sorts of turbulent effects into consideration right now as they're kind of doing their bench tests.
Hello. Hi, I'm from the Aerospace Technology Institute in the UK. We work with the government to fund R&D in the UK. So my question is, what's the sort of benefit, if you can quantify it, if you were able to apply this to a traditional single-aisle aircraft, and when might that be possible?
So this X-plane is a technology demonstrator. We'd actually probably never put this sort of flow control on this sort of vehicle. It's just showing that we can do it, and I think it will inspire flow control to be used in various ways on different platforms.
And you think it's very low maturity at this point in time, and it could take a long while to come to large commercial passenger aircraft?
Well, we've been waiting 25 years to actually get a flight test. I don't know how long it'll take to get on something that you can look out the window and see when we're flying. But it would be fun to see that in our lifetimes.
Yeah, thank you.
Hi, this is Jan Ludwig, Honeywell Aerospace. Thank you for a great presentation, exciting concept. How would you see the real implementation of the system in aircraft that would fly people? I mean, like the APU appears to be single point of failure. So how would this change for real deployment?
I think we have a couple talks in this section here that will actually talk to that.
Okay.
So I will defer to my colleagues, but you're going to have to stick around for another half hour to hear about it.
Sorry for jumping the gun.
No worries. We got one more question.
Saston, BA Systems UK again. How do you find the effectiveness of the technology changes when you ramp up the scale? So it seems like there've been previous vehicles tried at a much smaller scale. Imagine you've run simulations at various scales. What do you find?
Do you want to answer?
I can.
You were there.
There are scaling parameters that work pretty well, at least first order. Of course, you always have your Reynolds number effects or Mach number effects. Here, maybe more critical is the system scaling part of what you do in your wind tunnel. Can you actually scale that and then still fit onto an aircraft? So, so generally, the effects scale. If you can make the system work, that's good.
Are you going to talk more about it in your talk anyway?
It will come up in a qualitative manner in my talk. Yeah.
Well, let's thank.
All right, it is certainly my distinct pleasure to introduce our next speaker. His name is Fritz Langford from the Aurora Flight Sciences. He studied at Carnegie Mellon and at Georgia Tech. He is our chief engineer on the X-65, and he'll be talking today on integrating active flow control on an aircraft.
Right. Thank you, Martiqua. Okay, so my name is Fritz Langford. I'm the Chief Project Engineer for the X-65 at Aurora Flight Sciences. I am an employee of Aurora Flight Sciences, a Boeing company. I do not represent the US government, and I do not speak for them. Okay, so Crane, an X-plane for active flow control. I wanted to spend a minute talking about why AFC needs an X-plane and why the timing is right. Martiqua hit on a couple of these in her talks, that the confluence of technology development over the past 25-ish years of particularly computational fluid dynamics and additive technologies that she mentioned, of laying the groundwork for us to do the analytics to design an airplane like this. And then also the technology development of inside the active flow control community doing laboratory and small-scale aircraft has paved the way for larger full-scale applications. There was a question earlier, do the effects scale up? That is, in some sense, the key question this X-plane is setting out to show, to prove, and to demonstrate, and to answer the question. So one of the reasons this is a really exciting program for me, both personally and professionally, is that this is an aircraft that is targeted not at a particular mission, but at a particular technology. Everything about this aircraft, every design choice we have made, is about shoving as much active flow control into the airplane as possible. That's one reason that there are, we said 1, 2, 3, that's not nearly enough active flow control effectors. We're going to need 14 of them on here. One wing sweep, no, we're going to need 4. So that's the reason the airplane looks the way it does. Every design decision we made was made to maximize the learning that we can get about active flow control technology from this aircraft. We made a design choice about the type of AFC we were going to include in the design. As Martiqua mentioned, we designed in some modularity. So there are some on the wings, the actual little nozzles that the air comes out of are line replaceable units, so those can be modified for other applications, other ideas, future experimentation and learning. And then the wing tips, those outer wings, are actually removable, and then there's an interface, so a totally new outer wing could be fabricated, integrated onto the aircraft, and flown around. Those were all conscious and deliberate design decisions to maximize the learning for active flow control we get out of the aircraft, because, coming back to its purpose in life, as an X-plane, as a technology demonstrator to show the value of active flow control, to prove the AFC aerodynamic effects at a relevant size and scale, so that's moving up in both speed and gross weight, showing those effects, validating models, I'll come back to that, that's another key part of this, that the models, the design loop is a big, a big do loop, and that you need a lot of information at the beginning of design that you can really only get experimentally, and so you have to go all the way through, do the experiment, get the data, and then come back and incorporate that into design. So one of the things that we focused on early in the program was a set of design tools to enable future aircraft designers to include active flow control technology early in their aircraft design. And what we're doing here is validating those tools so that there's a set of results validating the tools so that when future aircraft are designed against those tools, there's a set of verification artifacts ready to go for when somebody asks the question on that aircraft, well, how do you know that this effect really scales at the conditions that you are claiming it does? The only way to answer that is with data. Someone's got to collect the data, and that's the purpose of this aircraft. So validating the AFC performance and sizing tools. The third objective, surfacing practical challenges, that is all the things you learn by actually doing. There was the session before this in this room was about the X-57, looking at distributed electric propulsion, and one of the panelists had a really great note, I thought, about the value of heading towards flight test, that even if you don't get there, just convincing everyone and going through all the steps and all the rigor required to get to flight test surfaces a lot of things, a lot of aspects of the design, consequences of early design decisions that you otherwise don't get. If you're planning for a ground test, maybe you aren't as rigorous about airworthiness, for example, or about some other aspects of system safety because you can keep people a safe distance away. And so you don't have to dig into, or you do not get the opportunity to, dig into some of those lower level decisions, and that's where a lot of the design challenges surface, and where some of the most important learnings to go into design decisions for the next aircraft are. And then the fourth thing we wanted to show and to explore was the integration of active flow control into the aircraft control laws. So this is an unmanned aircraft, probably pretty obvious. There's no cockpit. It's controlled by a ground station. It is fully autonomous. There's no stick and rudder. It's controlled by a keyboard and mouse. And consequently, all of the flow control test points are done with programmable test inputs. So there is a set of PTI that we have programmable test inputs, and so conditions are laid out, and that's how we actually mechanize the active flow control test points that Martiqua mentioned. So holding surfaces steady and turning on effectors, watching the aircraft trim out, turning on, fixing all of the control surfaces and flying the aircraft around, and then changing the control surfaces using the traditional control surfaces to change the shape of the wing, and then turn on active flow control and show changes in lift and trim as a result of that. So really exciting, and a lot of potential for the aircraft, and a lot of what we think will be really valuable learnings. So the punchline of this talk could have been active flow control is a new subsystem. And that was almost the title of my talk, because that is what I keep coming back to. Active flow control is not just a new technology, it's a whole new subsystem on the aircraft. We focus a lot on the effects of the flow control portion. The air exits the effector, it interacts with the flow around the wing. You get some force and moment, and you can use that for flight control, and that's great. But when it comes to integrating it onto the aircraft, it is so much more than that. It's not just the air exiting the aircraft, it's the whole journey of the air from when it enters the aircraft until it exits. And that's where a lot of those practical challenges start to surface. So if we walk through the life cycle of the air on the aircraft, it starts at the front. It enters this, well, it starts in two places in the front. So the APU right here, the auxiliary power unit, this is a dedicated unit. Its only job on this aircraft is to produce air for the active flow control system. We get thrust from the engine in the back. You're probably thinking, well, you could get air off of an engine, you just get some bleed air. You could, that's a design decision you could make. We'll come back to that. You need a lot, it turns out you need a lot of air, and there's probably a trade-off you will have to make if you do that, which may or may not be okay, depending on the design conditions that you're targeting in your aircraft. Okay, so there's an auxiliary power unit. It's producing the air. It's obviously not producing the air is coming in the front. It's compressing the air. So the air comes in, it comes in through the top here. There's actually, right here is the APU inlet. And it goes through the APU, it enters in the top, it gets compressed, and then it comes out and goes forward into this heat exchanger. The reason it has to go into a heat exchanger is that it is now very hot. It is coming out of a jet engine. It's about 200, 250 Celsius. My math is right. It's more than that in Fahrenheit. It's like 200, 250 Celsius. And there's a lot of it. It's compressed. So what we're really going for with active flow control is high mass flow. So there's high mass flow, which is perfect. If you studied heat and mass transfer, you now have a huge amount of very hot air that you need to push through all throughout your airplane. The airplane is probably not designed to have very hot air distributed throughout it. This is radiant heating is what it is. And so it gets distributed out to all of these effectors. So first you cool it down. That's the purpose of this heat exchanger. It's a ram air heat exchanger. Air comes in the front and then exits out here on the top. So the ambient is coming in and moving this way. The air out of the APU is moving forward, goes through the heat exchanger. Some heat gets exchanged, it's cooler. And then it enters into this distribution system. All of this stuff in blue, that's the AFC distribution system. They're pipes. And then it heads out into these control effectors out in the wings, and you can kind of see the shape of the aircraft here by where these are. There's some in the forward wing, there's some in the aft wing, some here on the outer wing, and then one each up here on the tails, in the V-tail. And that presents its own set of challenges, particularly on, well, I'll say particularly on this size of aircraft. I think realistically on every size of aircraft. There's now an extra set of stuff, of pipes and valves and valve controllers and these nozzles, all sorts of stuff you have to fit into the wing. That will affect the people who are doing the wing layout. It will probably affect structural penetrations. And the people who are designing the wing have to account for all of that and figure out how to deal with it. Which means you need to be pretty sure about where you're going to put these things early on, which means you need to know what the effect of the active flow controller is. You also have to deal with all of the normal things you deal with in an aircraft. These are pipes carrying very hot air. You don't want them to leak. You don't want them to overpressurize. And so you have to deal with that, and that implies you have to deal with the vibratory environment, wing loading, deflections, all of that with very hot air. Once you've solved all of that, you have to use it to control the aircraft. The punchline here, effector characteristics are critical to design, to understand very early in the design cycle because they will affect your control laws. I mentioned this is not a manned aircraft and there's no stick and rudder, so all of this is fed into the autopilot. The autopilot has a couple advantages. It's very fast and it can handle the nonlinearities. The point of these two charts on the right, the real point is, well, maybe just to orient, this is control authority for traditional and AFC effectors, specifically looking at roll control. So you're looking at P dot here so rate on the y-axis, and then the sort of surface or valve position on the x-axis. And the point here is for a traditional control surface, these lines are pretty straight. This is your traditional hinged surface. We have 14 of them, so there's one behind each each effector, relatively linear. This is extremely nonlinear. This is the AFC effector. The control law designers need to understand this behavior and need to know exactly where it happens. They need to understand this pretty well, and that means you need experiential data. We built a large AFC test bench, and we ran through a whole bunch of conditions on the ground to learn exactly how the effectors, exactly the closed loop performance of the system, of the actuators and the valves and everything working together, what that looked like, what the real effects were, and to understand the AFC system. So they're nonlinear. They're one-sided on our application. Clearly, there are other ways you could do it. Going back here, that would imply putting even more stuff in the wing. If you have either another set of effectors on the bottom of the wing, or you have a different, you're using some different type of coanda blowing out the back of the wing. There are different varieties, different styles of AFC. But at some point, you're going to be putting more stuff in the wing. That's going to be more weight. It's more complexity. It's got to buy its way onto the aircraft. They're relatively weak. The y-axes here are the same size in PowerPoint. If they were scaled to real numbers, this would be tiny. This is, which kind of makes sense if you think about it. If you cut off a piece of the wing and you put it on a hinge and you bend it, you get a lot of flow control. You can really affect the airflow around the wing by just by physically changing the shape of the wing. Doing that with a method like injecting some extra momentum into the flow to modify the flow around the wing, a little harder. You don't get just the force, the moment you get out of that you can use for control is just smaller. And so that makes sense. But the control laws still have to deal with it. And then probably the third and biggest thing, they're using a limited resource, which is air. In some sense, I guess that's true of hydraulics and electromechanical actuators as well. If you have a whole bunch of actuators, electrical equipment, you could bring down the bus. Hydraulic pressure is not totally unlimited. When you move a hydraulic actuator, you are using some of the pressure in the system. But generally, you have a big pump, and that's not a huge concern. For active flow control, here we're using air. The air is getting pushed out at high mass flow through these nozzles. And that's a limited resource. We can only produce so much from our APU, and you have to decide how to distribute that amongst all of your actuators. That has implications for using multiple actuators at once. It has implications for example, turbulence rejection. It has implications for maneuvering and sort of all sorts of things. Again, that's one of the reasons that the X-plane is so valuable, is to prove that this technology works at scale in those conditions. We think it will. We have the analyses to show, to justify why we think it will. And the flight data is going to convince people who aren't convinced by the analysis. Or it will make me look very silly. Okay, I would be remiss if I did not note that there are some extra system safety implications by adding this brand new subsystem. We talked a bit about distributing very hot air through the aircraft and the effects on that. This air is highly pressurized. It's running all throughout the aircraft. You're controlling the flight path. So this is the hazard that, the function here is controlling the flight path, presumably. Maybe you're doing something else with this air, but presumably you're affecting the flight path. That's the point of modifying the flow, which means that when you go through failure modes, when you go through a functional hazard assessment, you have a function, you have hazards against that. You have to think about that early in the design, because it drives back to the chart of laying out everything in the aircraft. How much stuff do you have in the aircraft? Key question, does it need to be redundant? This is a test aircraft. It's intended to test active flow control, so we don't have redundancy. In some sense we do, just because there's so much stuff in there. But we didn't design for redundancy. We designed to learn as much as we could about active flow control. So if it doesn't work, we'll turn it off and we'll say that was a fun thing to learn about active flow control, and we'll head back and reflect on the things that we've learned. On a production aircraft, you'll probably not have that luxury, and so you have to ensure that the system safety process is considering all the new failure modes that you've introduced into the aircraft and mitigating them. Okay, so practical AFC integration, active flow control can provide sufficient power for aircraft flight control. That was one of our claims at the outset of the program. We have analysis to justify that, and we are going to produce the flight data to show that. It's really exciting to work on an aircraft here that is going to that is demonstrating the validity of a new technology like this. So kind of a once-in-a-career opportunity that I'm really excited about, and I think others who work on the program are as well. It is a brand new subsystem, and there are characteristics that need to be understood very early on in the program life, in the aircraft design life cycle, that the data for which can only really come experimentally, and notably around the air source and the effector characteristics. So how are you going to compress the air, and then how are you going to get it out of the aircraft? On the right here, we have a diagram of some of the tools that we've described that we have developed during the and updated through the course of the program. I think Rene will talk a little more about that. But the sort of punchline is AFC has to buy its way onto the aircraft design. If you think about, like when I zoom out and look at big picture flow control on aircraft, we start with just the airfoil selection and design. That only gets you so far, so then you have to cut pieces out and move them around. That's like ailerons and flaps. Most airplanes have those, but not all. Well, most airplanes have control surfaces of some kind, so you can do wing warping too. But most airplanes have flaps. Then some airplanes have slats because just moving they're modifying it at the back isn't enough. You got to modify the front or some other high lift device. And then so you're moving through your design spectrum, and we're adding another step in that spectrum there of you don't have to modify any of the structure. What you can do instead is just directly modify the flow. And there's no free lunch. It is complex. It's a complicated subsystem to add to the aircraft, but it's really exciting to expand the frontier of flow control methods and demonstrate what can be done with a technology like this. And so just one more thing, as Martiqua noted, the aircraft is designed for modularity and for additional test points beyond what we're going to demonstrate on the Crane program. So there is some life and some modularity there to demonstrate for future work, to test different technologies, to expand the envelope and look at a whole series of different design conditions, validating these tools, new tools, test alternative systems, hardware. There are a lot of ideas on how to do active flow control. We had to pick one so that we could build an airplane, but it's not the only one. It might not even turn out to be the best one. And so we think it's useful for the community to have an aircraft and to have a platform to do more of that technology advancement on. And then the last point, I suspect as we learn more about these, we'll have to revisit the control laws. I think this will be a big area for the control field, and the control law developers will want to have a tool to do additional development on as well. And that is all I have. So thank you all very much. Thank you for coming, and I'd be happy to answer any questions.
Yeah, thank you. I have about 5 minutes.
Great.
Hi, thanks for the presentation. Norman Wood from GKN Aerospace in the UK. Do you have any plans to disconnect the command of blowing from a moving surface? I can't help feeling that some of your non-linearities are coming from the fact that you've put them on a moving trailing edge surface.
Yeah.
Those non-linearities would disappear if you had a pure circulation control trailing edge.
Yeah. That's a complex question.
It's a complex subject.
Plans. Fair. I would say the plans are limited by there's a huge trade space, and we have had to make narrow decisions for the current program scope while keeping the space open as much as possible for either to react to new information and new learning or for future efforts. So the aircraft can be flown, it can be flown with the control surfaces moving, so you can turn AFC off and just fly it with traditional control surfaces. That is one of the ways that we keep the AFC testing safe, is that you can always revert to that. Another is to lock the control surfaces, so you keep those fixed and you have the blowing over them. And then any other type of effector would be, so either injecting the air somewhere else or in a different manner would be a different effort.
Okay, maybe we can catch up sometime, because
Sure.
I've tested various options of those several years ago.
Oh, great,
And,
yeah.
and there's a lot of learning we could pass on.
Absolutely, thank you.
Maybe I can provide a quick comment. So the shape of that curve really depends on how you use AFC. So I believe what Fritz showed was you have a fixed control surface deflection, or even zero in that case, and you modulate through your AFC, right? Get stronger and stronger. That's where you get that curve. Other applications where you have just an on-off type scenario, so you just have your AFC on and you just modulate through your deflection angles, you will get that same linear response that Fritz showed for conventional control surfaces. So it really depends on what you're trying to do and how you're operating AFC. Is it on-off? Is it modulated? Is it for a fixed control surface deflection or for a changing control surface deflection? So there's a whole space. It's
That's a great point.
Yeah.
Thank you for your presentation. Witz Steczniewicz, Institute of Aviation, Poland. Do you expect transonic flow at the top speed, at the wings or some surfaces?
Sorry, the question is, do we expect transonic flow?
Yeah, like a shock wave on the wing.
Yeah, I think the idea is to, the short answer is yes. The idea is to explore in a relevant environment up to low end of transonic.
Have you made some ground test with these conditions?
Have we ground tested in
like,
transonic?
Wind tunnel test with
we have, yeah. So we've done a set of analyses. We've done some wind tunnel testing and some CFD testing to generate the predictions for the flow over the aircraft.
And the second question is, when the flow control is not working, what are you doing with the air from the APU?
Excellent question. When flow control is not on, what happens to the air? You throw it out the top of the airplane.
Excuse me?
You open a valve and you throw it out the top of the airplane.
Okay,
so
additional thrust.
You've got so you get so the APU, essentially you can turn off the bleed control. So you have control on the APU. That's another sort of interesting system safety topic on whether that's sufficient or if you need additional disconnects and sort of levers that you can pull so that you can always be sure about exactly where the air is going and make sure you have positive control over that.
And do you control the mass flow rate to the actuators during the pass, or this is just?
Yeah, great question. So there's a valve that is used that opens and closes and is used to control flow rate.
This is like a general valve, or you control each actuator separately?
Each actuator is independently controlled.
Okay.
Yeah.
Thank you. This is Pradeep Raj from Virginia Tech. And enjoy the presentation and a couple of quick questions.
Sure.
What do you see as your biggest risk as going forward for the flight test program?
Time and opening of the there are a lot of, at every point in the design, we have had to make decisions, and it is not always obvious what the right answer is, and it is, and in fact, the more you dig, the less sure you are that this is the right answer. But the purpose of this program is not solely analysis, it's to validate the analysis tools. And so it's a delicate balance between ensuring that we have done an appropriate amount of thoroughness and rigor at each part of the aircraft, particularly around things that are not related to active flow control. The purpose of this aircraft is to demonstrate active flow control. None of it flies until all of it flies. And so every other subsystem, including the ones with off-the-shelf components, standard work, that kind of thing, all of them have to be robust. They all have to pass airworthiness. They all have to be proven to be safe. And there's a limited amount of time, and so decisions have to be made sort of cleanly, but quickly.
Just in the interest of time, I can talk with you offline then.
Sure.
Thank you.
Thank you.
Thank you. Thank you.
Thank you.
Okay, let me introduce Rene. Dr. Woszidlo has a PhD from University of Arizona / TU Berlin, and he is at Boeing. He's in a fellowship, and he's our SME subject matter expert in active flow control.
All right, welcome everybody. Thank you for hanging in here, close to the end of the day. So I will take a lot of what was already said and kind of zoom out a little bit and try to address this question of why has the technology not transitioned yet? We already heard there's been a few decades of great work, great progress in that area. So lots of demonstrators at different scales, different sizes, for different purposes. Lots of work in academia going on. So we've kind of hit this, this wall. Why has it not gone beyond that wall to actually transition onto an aircraft? So in order to address that question, I'll be talking about these four different areas. So applicability was already mentioned, right? Does AFC do what you need it to do, right? What is the mission that you're trying to address, right? Is it maneuvering? Is it high lift? Is it other applications? Second one, scalability. That was already brought up, right? Does it actually scale from a wind tunnel scenario to a real aircraft? Aircraft design, I'm gonna spend some time on that. I think that's really the biggest differentiator of how we should look at transitioning the technology. And then finally, like maturation, right? So we've heard the comments that the technology has matured quite a bit. Is it mature enough to transition onto a future aircraft? So with that, let's talk about applicability. So everybody who's working in flow control, right, has probably seen those curves on the top right. Here's my favorite AFC device. I put it on a wing or an airfoil, and my lift curve shifts, either just up or to the right or something in between. So the question is that usable? Can you actually take advantage of that effect on a real aircraft? So, for example, high versus low angle of attack. So if you claim great success at high angle of attack, but the aircraft never wants to fly there, then you kind of are lost there. Then control surface deflection, mentioned that in an earlier question. Do you have AFC for cruise conditions where you have 0 degrees or close to 0 degrees control surface deflection? AFC may not do a whole lot at that angle. So you want to keep that in mind. The second part that I've learned to appreciate quite a bit, especially through the crane program, was can you actually control the effect? So you see a lot of great research coming out where there's great deltas right? 50% lift improvement if you follow that curve, and great claims that you can see. But is it actually stable? Like, can you actually fly and operate the aircraft with those effects? And do you have the control loss to handle that? Or is there some other penalty that you are not considering? So especially trim penalty. So just having more lift doesn't necessarily always buy you a net benefit. So that's the aerodynamic effect part of the applicability. So AFC integration, what has come up, and I'm really glad to see that that is becoming more of a focus. I think a lot of people recognize that, yes, AFC has a great effect aerodynamically, but now how do you actually put it onto an aircraft? How do you integrate that into the leading edge of an aircraft? If somebody proposes AFC in the leading edge, how do you integrate it into the trailing edge of a wing? So those are all very important considerations. So especially if you were talking to somebody like a program, right, whether commercial or military, you need to be able to answer those questions, right? So just the aerodynamic effect, typically when I talk to my colleagues, we're pretty quickly beyond whether I trust or believe the aerodynamic effect. It's really the questions of like, how do you integrate it, right? What are you going to do with it? What happens if it fails? So the penalty was mentioned, space, weight, and power onto the aircraft. So is there a net benefit? I'll talk a little bit more on the aircraft design side about that. And then is there a suitable power source for that, right? So we have an APU on the Crane aircraft that's very, it's a very heavily sized system to demonstrate on Crane. But what would that actually look like on a real commercial aircraft or real military aircraft? What can you leverage there? So at the end of the day, the bottom line here is not every AFC effect is useful during flight operation, and that has to be kept in mind when we do research or discuss research in those areas. All right, so next part is scalability. So that's one of my favorite pet peeves with some of the proposed AFC methods. And we learned that quite a bit here on Crane as well. So on the top right, if take your favorite AFC parameter, whether it's the momentum coefficient, whether it's the power coefficient. So there's three factors in there. So to the right here is the Mach number ratio. Most wind tunnel experiments that you see in the literature are, university scale wind tunnels, maybe around Mach 0.1, maybe 0.2. So if you scale it up to relevant conditions for an actual aircraft, that ratio goes up, or in order to maintain that ratio, that jet Mach number would have to go up by quite a bit. That's not always feasible, right, depending on what kind of device you use. So I show that here. Realistically, you might be at choke conditions, have Mach 1. So now in order to maintain these scaling coefficients, you have to balance that out with these other variables. Number one is pressure ratio. So pressure ratio in a lab environment is great, right? Shop air, just hook it up, press the button, get a lot of air. And the air is typically room temperature. So how do you do that on an aircraft? So Fritz was already hinting at that, right? If you have an APU, that's hot air. So you got to deal with that. If you wanted to use bleed air from the engine, which is certainly a desired source of compressed air, that's also very hot the higher you go in pressure ratio. So you may be very limited of how high you can actually push that value. So now you're left here with that last one, the jet area or the area ratio, where how many orifices do you put on the aircraft? How big do you make them? It was brought up earlier, right, with rain. So if you have huge holes somewhere on your aircraft, you have to make sure they are not, just running full of water, or, other integration challenges with that. So, and I want to be clear, I'm not implying that it's not feasible. I mean, we scaled the system for Crane for up to Mach 0.7, so that's a very high Mach number. Many other applications are typically only up to Mach 0.2, Mach 0.3. So it's certainly possible. It's just something that has to be kept in mind when doing early research in that field. All right, so next one, aircraft design. So this is probably the biggest change in philosophy that has surfaced over the last few years. That traditionally, as I think Martiqua mentioned it earlier, AFC has been brought into a lot of applications here in that preliminary detailed design cycle, right? And typically how it went is program designs an aircraft, goes into detailed design, tests the aircraft, oh crap, there's a problem, right? Aerodynamically, there's something that we can't deal with. Oh, hey, can AFC help? Yes, AFC can help. And showcase that in the wind tunnel and CFD, works great, but then now you also have to deal with penalties of it. So now those penalties are not attractive for that program. So there has to be a way of getting into the design cycle early on here on the very top level. So are there very fundamental approaches where you can insert AFC as an effect and as a penalty into the design process? So I often refer to what's the thin airfoil theory of AFC. So we're hoping to make some progress of that and developing some of those fundamental tools with that. Done some work on the flight test. So crane is a perfect example. The vertical tail flight test in 2015 was another great example of at least showing the scalability of the effects. But there is that system design integration. We heard a lot about that, the hazard and failure analysis. Right? That's a huge aspect. It's like I always get that question, what if it fails? What if the system doesn't work? What happens then? It's like, yep, that's a valid question, and happy to work through that engineering to answer that question, but that becomes very application specific. So long story short here, for the design process, AFC requires different tools for conceptual aircraft design so that you're moving that red box here from the middle up to the top into the conceptual area. All right, so what would that look like going through that process? So I already mentioned AFC has been typically considered as an add-on to an aircraft design. You get the system penalty in addition to the benefits, but now you kind of fail to provide a compelling business case. So the program is going to look at this like, all right, there's an unfielded technology that yes, will solve my problem, but also has a penalty related to that. Do I really want to take that budget and schedule risk on in my mature program? And that's typically where it stops. So getting into the early phase of a program where you really have the conceptual design phase is much more enticing because you can make for a better, compelling business case, technical case for the technology, and then you got a seat at the table, basically. So once you make it out of that conceptual design phase, now we can apply all the expertise that's out there in the AFC community to really optimize the AFC. So now you have an aircraft that takes or took AFC into account, and now you can play around with all the variables there are to make it as the most effective, most efficient system on the aircraft. So what that would look like here on the design side is you start with a set of mission requirements, right? So what's your aircraft supposed to do? And then you design two aircraft. One is without AFC, conventional methods as are currently out there, and then you design another configuration with AFC on. And they are not necessarily the same. They're very likely not the same. And now you have an apples-to-apples comparison of not, two different designs, one with and without AFC, and you compare it and see which one is better. And not that you take a design, then add on AFC, and then try to compare it, which typically doesn't work out well. So punchline here, AFC is less likely to transition if added to an existing aircraft design. There was a paper a year and a half ago at SciTech that we did. It was a crane special session. I think there was 3 sessions actually. There's a paper that showcased some of the conceptual design studies that we did, and across the board, there was always a net benefit. Especially if you had a very constrained design space with, for example, low speed, high speed requirements. So the more difficult your design space was, the more benefits you would get from using AFC. All right, so what we did under Crane, you saw this picture earlier, we split this up into 2 parts. So you take 2 tools, 2 models, one that models or predicts the AFC effects, right? Gets you in the ballpark. How much is the rough order of magnitude delta aerodynamic coefficient that you can expect from AFC? And then you add that together with the system side, right? It's an air distribution system, ain't rocket science, right? So you got a source, you got air that has to be plumbed from A to B, blowing out through some orifices, and you add that all up together. So what is the penalty that you would add to the aircraft? And you tie that all together under some MDAO framework, conceptual aircraft design framework. Now you have a way to trade AFC early on. So we did it as part of Crane, and we've only kind of scratched the surface with actually exercising those tools. But just a realization that these models were needed and at the appropriate level of fidelity, in my mind, has been one of the greatest accomplishments already out of the Crane program. So. All right, so what that does in terms of developing a business case, an add-on is just, it's a fixed design, you add something on, right? A benefit and a cost, as I already mentioned. So if you tie that into the aircraft design cycle, we've really seen these cascading waterfall effects of a technology. So if you account for both the benefits here in green and the penalties in this brownish color, and you run through these design cycles, and so it's the spiral development of, let's say you get more lift, you can make your wing smaller, but now you also have different structure weight. You have the weight of the system, but now you have a smaller wetted surface that would then have less drag and cruise and so forth. So there's this cascading process that goes through, and so far what we found is that you get a net benefit with that, right? It depends on the design, yes, on the type of aircraft, but overall I was even surprised myself that across the board it was either like even or there was a sizable net benefit. So it was very encouraging. But just taking full account of both the cost and the benefit, I think, is crucial in this early conceptual design to get on the books with the technology. All right, so I'll get to the punchline here. So I personally believe AFC is on the right path to transition to future aircraft with the programs that are currently ongoing, with the tools that we either have developed or are developing. I think there are a lot of new aircraft programs ahead of us, whether on the commercial side or the military side, that there's a lot of opportunity to insert new technologies. And I believe AFC is one of them. And so far, we've been playing in that center box here, AFC optimization. We're getting better at addressing AFC system integration, but we really need to move in that sphere here on the left of having validated AFC design tools to insert into conceptual aircraft design. So with that, I hope to, I don't know who said that earlier, but in our lifetime, seeing transition of this technology onto a future aircraft, and I'm optimistic. All right, with that, that's my talk. Thank you. Lady here in front.
Hello, I'm Thalita from Boeing Brazil. So I wanted to ask, because you said that you developed some ways of comparing the system, the active flow control system with conventional airplane. So these tools that you develop also apply to comparing like a blended solution that you could kind of use some things from a conventional airplane and some things like putting active flow, for example, on the, I don't know, on the elevators, for example, or anything like that?
The tools are agnostic to platform, so it's just that there's some fundamental wing shape parameters in there, but yeah, you can trade it on the tail, you can trade it on the wing, and then you just, you know, add it all up together and to flow into the overall aircraft design and then see what comes out of it. Depending on the configuration, depending on the requirements, you may find that it's more efficient to use it just on one or the other. But now that we have the tools, or at least a start for the tools, you can actually run those trades, right? And say, hey, do you hit some kind of plateau, right? Just putting AFC on everything is probably not gonna be good.
And you can actually kind of simulate or those are to make it possible for you to evaluate on each flight phase. For example, on cruise, it's better to, as you said, that the angle of attack does not change that much. So on cruise, it's better to have the conventional airframe, and on takeoff, for example, it's better to do active flow or something like that?
Yes, you can, and that's just depends on how your MDO framework is set up. So you basically leverage what is already out there. So whether it's commercial, defense, however they do their aircraft design process, this is like an add-on into, like the tools are an add-on into that process. And yeah, regarding cruise or more low speed, there's some obvious trades, and yeah.
Mujib Malik from NASA Langley. So what is the fidelity of the CFD tools that you use in these tool set? And how confident you are that you are capturing the right physics? Because without that, it's meaningless to do this.
So they're not CFD tools. And it's conceptual aircraft design, right? So even without AFC, the fidelity of the tools may be questioned, right? Whether you use an inviscid panel method, right, to size an aircraft. So the tool that we have is an empirical tool, and it was validated against wind tunnel data, high fidelity CFD. We also compared it with a crane configuration, and what we found generally is we're very good, like in the ballpark, right? It's not sufficient to build up an error database with it for a control law or something, right? But from a sizing perspective, to see what order of magnitude can you get from it versus the penalty that you have to pay for it, it seems very well aligned with the tools that you're already using in conceptual aircraft design. So once you go to the detailed design, right, then of course you can have that conversation with RANS tools or DDES or LES or other CFD tools or wind tunnel tests, right? But I think we have pretty good experience with that on the detailed design phase.
Carlo Cordoni, Politecnico di Milano. For the X65, how did you make the conceptual design decisions about, for example, the sizing of sweeping jets, the spacing, the conceptual design choices?
I guess I'll take it, yeah. So we had some early wind tunnel data with AFC that kind of got us in the ballpark of how much actuation output do we need to be relevant, and then size the system accordingly. So like the APU, for example, was informed by, okay, we need roughly that amount of mass flow, what can provide that, and we found that APU and stuck it on the aircraft. So in terms of spacing, that was actually pretty straightforward because, as I mentioned earlier on my slide, in order to scale that output to the higher Mach number, the only lever that you're kind of left with is the exit area. So of course you can't just have one big hole, so you just do more of them, and so you space them tighter. So that was pretty straightforward. It's a fairly dense distribution of jets just to have a sufficiently sized system for that Mach number. For conceptual design, you don't care, right? Like in conceptual design, you don't lay out like, oh, I want my jets to be at this location, at this spacing, at this orientation. For conceptual aircraft design, you just need to know how much delta can I get and how much is the cost for it. But then once you get from there in the optimization side, that's where you can play around with all these variables, and that's where the community is really good, right? I mean, that's what we've done for decades to go through all these variables. Yeah?
Once again, this is Pradeep Raj from Virginia Tech. I'm just curious, the tools that you mentioned, the empirical tools, is there any sensitivity to the type of active flow control you want to use, like steady, unsteady, or electric or pneumatic, or that kind of thing? Thank you.
Short answer is yes, but maybe you give a similar answer as I just gave before. On the conceptual aircraft design, I don't care. And the assumption is, do I have a well-designed AFC system, right? So I went through my favorite experts in AFC and say, hey, how would you put AFC on this vehicle? And would you use steady jets or sweeping jets or synthetic jets or whatever? And that's how we produced the data that went into that tool. So it gets us in the ballpark. So there is some underlying expert knowledge that we started with an AFC approach that was promising, right? But yeah, you can tailor it to other AFC approaches too, but at least we have a starting point. Yeah.
My only concern was like swap the weights.
Yeah.
Could that be a major factor?
It is, right? Like steady jets, sweeping jets, you have different pressure losses, you have different mass flows maybe, but still and I even have to be honest, I was still surprised even with fairly conservative approaches on the effect side and fairly conservative approaches on the swap side, that we still got a very noticeable net benefit that can only be optimized further on, right, with all the variables that are out there that you can tweak. But just getting us on the field to play, right, is the difficult part, or has been the difficult part, right? And yeah.
Thank you.
Yeah.
Best of luck.
Thanks.
Okay, one more question.
I'm Lucas from Limbra. A small question: does the tool only compute the aerodynamic effects of the AFC, or does it impact the system effects? An example, when you use the FC, you will get an increase in the aerodynamic performance, but you also increase the engine bleed. Does it make this ponders the opposite effects on the aircraft's performance?
Yeah, no, very good question. And if you recall the slide that Fritz showed earlier with the effectiveness curve, right? You have kind of this linear regime where you get increasing effect with increasing output, and then kind of plateaus off, right? So once you get into that plateau area, you're not getting a lot more benefit, but your cost will go up more and more. And so I would look at my MDAO colleagues, it's like, hey, if you're doing a good job with your framework, you will pick out those optima.
And we found that to happen. So in the MDO process, you would sweep through both of that, the effect and the cost side, and you would find that, hey, there's only so much you can get, and that's the whole purpose of using that MDO framework to find those optimal.
Okay, thank you.
Okay. Thank you one more time. Okay, it's 6 o'clock, and next speaker is Daniel Reckzeh from Airbus. Daniel currently is a senior manager in the Airbus technology program, and prior to that he was responsible for several flow physics programs, integration programs, particularly the A350 trailing edge multifunctional wing.
Thank you. Thank you, Paul, for the introduction. So, inspiring stuff. So happy to put, so to say, some perspectives really here now. Airbus, obviously, here, commercial aircraft, the application perspective on large transport aircraft, which is something I would say quite particular. Beyond, or maybe as a sub-range of the bandwidth on what you have here opened up on the principle appealing potential of what active flow control could yield. But of course, active flow control is something which we currently have not in our solution range, which we have not as a key on our piano, I would even say. So only to remind, there is of course also in our parameter lots of consideration. What is active flow control? Here it's deliberately not dealing with active flow control for drag reduction. I'm stressing this because in our discussions there were even the points, couldn't there be a multifunctional way? If you do hybrid laminar flow control, couldn't you use the compressors even for low-speed separation control? And then it's going wild if you don't even know on the specific optimization of one of these solutions. But it's something where you see that it triggers dimensions. So, why is this AFC, as I defined it here, in terms of reduce the tendency flow separation, enhance the flight envelope, the effectiveness of controlled surfaces, or treatment of complex flow separation? Why is this not yet even considered to be used for large transport aircraft? So this is a range of reasons, of course, you could consider. It's missing aerodynamic performance, people may suppose, and therefore, of course, maybe the question, you nicely have given this point, does it pay off in terms of the overall aircraft performance? Can you really mature it something under the bottom line? And then everyone is scared if there's an additional system coming up, failure cases, how to treat it, how could it fail at all, and what does it mean? Cost, manufacturing, maintenance, something which is playing, of course, on large passenger transport aircraft an extremely important role, and usually is the spoiler for many of the technologies which we have considered over the last decades to potentially bring them forwards. Reliability up to certifiability, and finally also fear on the unknown. It's of course a product where the amount of risk averseness is there with good reasons. So in the end it's everything, and under the bottom line also of course is a key point, simply not knowing, as this is something new which we have not done before, where we cannot extrapolate out of what we have done before into maybe more targeted applications on a next product. So, of course, we have done some work, and here it's really also to stress it, and you will see it in the footnotes. Maybe we are the least knowing ones in this parameter, so there's a tremendous amount of work done together with partners, and some examples will be shown. Partners in national and European funded frameworks, and this is something where, so to say, we as an industry really try to stand on the shoulders of the academic and the research community to show the way, and then, of course, play the views in terms of how to then wrap it all up in a realistic product environment. So today's view after many years of research, so it's quite some years which this is going on. SAFC is not new at all. It's flying on fighter aircraft since the 60s. But this is not the kind, of course, what we consider as realistic applications, potentially realistic applications, or reasonable, I would call it here, with our view as of today. So these 3 points here, or maybe even elaborating perhaps a bit more on the picture. Of course, full span AFC instead of a slat or a flap, all these studies were done, or AFC enhanced flap, where finally you find no room for load carrying structures anymore. This was all converging down to the point that we say, okay, yes, with targeted manipulation on the flow, you can really enhance the effectiveness, for example, of trailing edge flaps. Or quite comparable then, not only for the flaps for takeoff landing, low speed performance, but also the primary flight controls on the tails or on the outer wing, ailerons, rudders, elevators. This is something where we see there is a considerable effect. So enhancement of given control surfaces. What also has shown to be quite interesting is application on outer wings. You know that, of course, nowadays aircraft have the tendency for quite non-planar outer wing designs. And there, of course, if you need a means to protect maybe from premature flow separation, this is something which you can perhaps better integrate in a curved winglet design than a leading edge device in a classical mechanical way. And then one point of considerable importance which we have found, and therefore I will elaborate on this in a minute a bit deeper as a use case, is power plant integration. So this is an example case where we say, okay, why power plant integration here? Because it's something where we not say, okay, flow control as such is an alternative to what we classically have on the aircraft, but here flow control, and this is so to say the line on which we further elaborated, is an enabler to overcome design problems which we simply didn't have in the past. Otherwise, maybe flow control would have been already on our configurations. But one of the key reasons why it's not there, it was simply not needed so far. Now, of course, we have the tendency for integration of different, more effective propulsion concepts, ultra-high bypass ratio engines, open rotor engines, large nacelles, and if you not yet say, okay, make a high wing or an extremely extended landing gear, you have to overcome these integration challenges. And there are lots of, I would call it dirt areas where we have premature flow separations, where there's no easy means to put a strake there or leading edge device there. It all does not work anymore. And it is compromising the low speed performance of the complete configuration in a dramatical way. So flow control could be a means to overcome it, alternatively to really putting complexity on the aircraft elsewhere in order to maintain the required performance. And this integration area was something where I say, okay, target this as a kind of, here's the idea, and then we characterize what is the problem. We find out together with partners a solution, and what we develop here is not yet maybe a product solution, but it's simply knowledge. So this is how to illustrate it here, and the outcome of the knowledge is something which you see on the right. This would be reasonable, this could work, so therefore maybe let's target on further exploration on this one. And this is, so to say, the hottest topic out of what we see, but by far, of course, not the only one. And of course, as a convergence to future efficient engine configurations and how to integrate it is by far not sorted. It is something which could be a contender technology, but nothing which we currently consider on the forefront. Now the point already came up, what kind of AFC could you put on your aircraft? As a chief engineer would say, something which is not weighing anything, which is having ultimate performance, not requiring any additional subsystems. And there is, of course, a range from steady blowing actuators over these pulse blowing actuators down to synthetic jet actuators. So minimum integration impact, maximum effectiveness, you don't get it, of course, on a single solution. So therefore, it, of course, has to be the trade-off. And this was something where in these partnerships, a lot of knowledge has been generated, that there is a way, maybe on pulse jet, which is perhaps, I wouldn't call it a sweet spot, but maybe suggesting that these are feasible solutions, where you don't need a big power station in order to provide bleed air in endless amounts, which, of course, you have to carry around on the aircraft, and it is compromising really your overall solution, because you put a heavy machine on there for maybe then something where classical means, even if high-hanging fruits, are perhaps equally attractive. So therefore, on this pulse jet blowing actuator, this is something where, of course, all these considerations, how to further integrate it, have been maybe focused. But of course, these others, especially maybe synthetic jet actuators and so on, there could be also alternative means. So let's see what also maybe beyond what we may trigger or require is coming out of the academic, out of the research pipeline, even maybe from complete different applications than classical aeronautical ones. Yeah. important and mentioned before, make it technology ready. And now you would say, well, there have been tremendous things already done, but not in a way that it's an integrated solution. It's an, say, maybe conceptual solution. It is something where you have demonstrated that it works on a representative geometry, maybe even representative dimensions. Maybe you have also done some trials there on realistic actuation concepts. And finally you would say, okay, then fly it all, then it's TL6. It is not as simple as that, because TL6 in industry context would of course mean that you have considered also maybe the overall integration loop on the aircraft. So then it would end up somehow in this valley of death, which you have shown before, and this is something where the question is, okay, how to trigger it at least that far, that we are maybe not yet entering it, but in case it's attractive, how to overcome it. And there, of course, integrated, also large-scale demonstration is required, not only maybe to prove it in a classical way, but as maybe the next product decision is not only done in the brain of the chief engineer, but especially for some maybe higher risk technologies, also in the belly, it is something which is advisable to be conducted simply to be convincing that this is not black magic, but that you can do it. And this was something like, as you mentioned, the A350 wing, this multifunctionality, this was something where demonstrators, which were at the time when we decided on the concepts, they were simply flying on the other side of the runway in Toulouse, and therefore suggesting the view that there is a certain fidelity and this is not crazy stuff from crazy aerodynamicists. And this is something which we really need to trigger here. And there are, of course, elements which have been put on that track already, which still concludes in a way, as I've just shown you, there are reasonable potential applications. So going along that track, here are some examples on proving it first on representative geometry. Does AFC really work on this sketch problem? Engine integration, cutting back the sled because it simply does not fit there with this very high bypass ratio, close-coupled engine. Optimizing maybe an active flow control system via CFD to see is there an effect at all, with all its deficiencies in these predictions. Nevertheless, showing yes, it could work, putting it in a wind tunnel and show it, yes, it works. And there, of course, now you have to somehow represent it, smaller scale, and this question, of course, was already triggered. This actuators and the wind tunnel, does this have anything to do with what you would then fly on an aircraft? Is this scalable? Is it comparable at all? But first, and I'll show you in a second, of course, to elaborate that this trade-off between the various actuator concepts, this was interesting to see, because you first saw, yes, more helps more, but of course more costs more. And then the question is there then the alternative way, which is from this heavy, steady blowing actuation, suggesting that this pulse jet actuation may be best compromise between effort and gain. And this is a picture there in the middle, where you see the change in maximum lift coefficient over the blowing coefficient. There is, of course, a considerable attractiveness of this pulse jet actuation. And this is something where, of course, now you could say, okay, try to scale it up in order to really believe it. And then, of course, consider what is a real actuator there. Not only for the aircraft finally, but also even to demonstrate it, not only on representative dimensions for the arrangement, but finally, of course, also a representative real actuator on these representative dimensions. So this is a very large-scale test which was done there several years ago already in order to say, okay, then simulated more or less one-to-one and comparable flight conditions to real aircraft in low-speed operations and put the real system in there and demonstrate that it works. And indeed, this was something which was providing not only the surprise that it works, or the non-surprise that it works, this was somehow, of course, expected, but it is something where, of course, you could now really check it out in more detail. What are the behaviors, the flow conditions, what is really the full-scale actuator behaving like in order to believe it really not only in a phenomenological way that yes, there is an effect, but also to cross-correlate where it's coming from and then saying, okay, this is another step in the range or in the ladder to build further confidence. And now, of course, the question is how realistic is this actuator? There are, of course, say, laboratory kind of actuators, where you say you don't get this on an aircraft. You cannot integrate it because it is simply not possible to reserve that space or to provide that power supply. And this was a long time really a question, is this the showstopper? And the way which we found was finally, okay, with all this complexity to build these actuators, to manufacture it, it is out of question. This is not industrializable. And here, the third way suggested, who knows whether this is finally then really a solution, was doing it with additive layer manufacturing instead of, I don't know how many 100 parts, really accuracy milled and then integrated, glued, bolted, whatever, simply make one part. And this is then the actuator which you put there as an insert, really as a kind of 3D printed element. This is interesting because there was a hype of 3D printing in aeronautics. Why here? Here, because the complexity simply pays this off, and it is not something when you need hundreds of parts on an aircraft where classical manufacturing principles are maybe superior. But for this highly complex part of this kind of actuation concept, here this ALM was considered as a way out, where otherwise we would have stopped already with the question, can we do an industrializable actuator? I don't go deep on this because this was nicely elaborated. It's of course not an add-on where you say, a bit of aero performance could help, but you have to consider it really in the overall concept definition loop. So we know, yes, it works, but the question, which is of course not then easily to be answered from what I've shown you there, is the solution really feasible, and more important, or equally important, is it superior on overall aircraft level? Does it make sense to go that way, or are there alternative means which are less risky, where you have maybe, again, not the brain, but the belly of the chief engineering, which feels a bit better in order not to bet the future of the next product line on such a technology? And therefore, these integration studies and trade-offs are crucial from the start of the technology development. Not do this last, but do this more or less even first. And therefore, you have shown, of course, really appealing examples here. So, how to integrate, of course, and take a real aircraft and say, but behind the front spar there is no space because there's a fuel tank or whatever. So you have limited spaces, and then design into these limited spaces, or turn it around, say, if we do it right from the start, then of course, there is a question, can we adapt the overall wing layout, really in terms of wing box structural consideration, size of the fuel tank? Can we adapt it in a way to make AFC more viable, or is it integratable simply in constraints as of today? You don't want to pile up risk on risk on risk on a future product development, and therefore some of the constraints probably shouldn't be challenged, rather target the AFC system to make it fit in order not to have everything uncertain on a new overall wing or tails layouts. And and then the question, and this is where we are currently scratching our heads still, is this certifiable and is this operable? Everything can happen like on a normal system there, and this is an additional one where no one has really this operational experience. Broken pipes, blocked valves, detected or even undetected loss of the system, symmetrical, unsymmetrical, whatever. And then the question how to control it, how to detect it. Now additional sensors needed to monitor the system. They have to be reliable also by themselves. Difficult really, because complexity adds on complexity simply in order to control this complexity. Loss even of the primary power supply for the AFC. If you not have a compressor, but maybe then really using engine bleed because you maybe didn't want to put much additional add-on systems here, so you would strive for really using maybe in a synergetic way what is already on board as energy provider on the aircraft. Even that can fail. So failure of the AFC system obviously has to be treated like a failure of flight controls, considering that, of course, on that aircraft you still have the complete bunch of classical flight controls also still on board. So on top, smart solutions could, of course, hang this fruit rather low. I don't claim that this isn't necessarily an absolute showstopper, but it is something to be considered right from the start there. And then, if you say, yes, we can certify it, tick in the box of the certification document for the next aircraft, is this something which the operator, the customer wants in field? Is this something on harsh environments, daily operations, in context to classic or to normal maintenance intervals? Is this something which you can really sell there, even if it has a benefit? So cleaning of the AFC system, in-field maintenance. What about icing really in operational conditions, or even if the aircraft is standing overnight? Drainage system already mentioned. Is this needed here? The aircraft is standing in the rain and ice and whatever. You have to somehow design it there. Is this a showstopper for such an actuation system? Impact of dust and erosion, and maybe also operational aspects, even if you say, this should be the minor problem if you really can do appealing performance enhancement for the aircraft. But if it has cabin and ground noise on such a system, it may scare the passengers, and the chief engineers may say, no way, but I don't want to have it here on the aircraft. And then, yeah, if we are there and say, oh, it could be attractive, but not enough, and now we have to optimize. But are there further parameters which we can optimize? And there is a tremendous amount of parameters which we even somehow didn't study in a way to further optimize. It's the number of the jets, the spacing between the jets, the pattern of blowing, constant or pulse, as said, all at the same time traveling ways in spanwise direction. Extremely interesting results on the duty cycle reduction. So reduced, of course, the need of pressurized airs, less offtake, and then you get somehow in a beneficial scaling process, yeah? And there's so many unknowns, so much need really to do this parametric research here. So how to do it? Because in the end, we are not the ones having all this knowledge here as the OEM. And this is something where you say, okay, then like maybe with other technological solutions, try and error, use our engineering experience, and then build trust in a kind of targeted understanding, qualitatively even. But now we have novel means, of course, in hand, improving the accuracy of the simulation, not only numerical, but also experimental, of course. And then, of course, really maybe hope for the next generation of even better prediction tools instead of getting lost in the wind tunnels of the world there. And finally is to say, okay, can we master this in our engineer's brain, or do we have really different patterns in order to optimize it there in the machines? So, some considerations, as I said, it was done before, it was flying, but of course by far not applicable for any safe operations of a transport aircraft with passengers inside there. So far so good. Yes, AFC is technically, mainly I would point it here, aerodynamically viable, and it shows benefits and still significant room for optimization of the key parameters. But this long and winding road is something which we really have to address, because from our considerations, by far not yet product ready for any civil transport aircraft. And one nasty thing is that, like for other technologies, integration constraints usually compromise the principal benefits we are discovering. So how much is getting lost, how much is still remaining? Does it make sense at all after considering all these real-world constraints here on that kind of product? It would put a new paradigm for functional components on the product, and this is something not to be underestimated, even if you prove it in a technical, valid way. But the required route, new route to certifiability, something where you have to take the authorities on board right from the start, because if they say we don't sign this, you cannot discover it when you say now here I want to certify the aircraft after 5 years or 7 years of design and development. This has to be considered right from the start, even defining what means of compliance against which certification rules we have to provide. Nothing there at all there. And then, of course, the industrial colleagues down the corridor, manufacturability, operability, and, as I said, also customer acceptance. So what we see, AFC could be a third way, really an enabler for technology potential which otherwise may be non-reachable or very difficult to reach, like this integration of novel, highly efficient engines, or also, as we had several lectures addressing it already here, high aspect ratio wings, very slender, very, say, curved or flexible. Maybe classical movable devices simply do not fit on these anymore. So in the end, who will be the leader of the pack? You look on industry because you say, okay, out of research and academia, you've put it on the ramp, and now you say, okay, make a product out of it. I would still point back and say, as we not can foresee that an extensive application of AFC on the next generation of civil transport aircraft is likely, so it still requires this research. There has to be further fidelity to provide it to all disciplines, not only for aerodynamics, to mature in time for the product after next. And this, of course, not necessarily means that it still takes decades. So research establishments are the competent and appropriate place to further lead this. But industry, of course, now is in the duty to guide this into product applications, not to not indicate what industrial or certification requirements may play finally the crucial role in order to make it happen. So there is a duty on industry really to point directions or raise a finger in order to steer what is really required as further research. And of course, as you have shown it, there are highly interesting new opportunities which may come up and accelerate perhaps the readiness in an innovative way. AFC applications on UAVs, or also maybe military products where different standards apply. This may boost the maturation via the direct product applications, and this experience, this understanding, this confidence may then really be harvested also in the application of the civil transport aircraft. So there is a need to further innovate, develop and mature this long-term technology in partnership, and we are of course looking forward. As I've told you, there were these footnotes who all has contributed there, and we are standing somehow on the shoulders of all these contributors. There is a need, and really the underlined invite, whatever you may call it, from our end to further progress that way in order not to get lost in this very nicely illustrated valley of death where definitely active flow control shouldn't get lost, as the potential which we see in principle are high enough to boost it over this valley of death. Let's see when and how, but I'm personally still positive on this and therefore let's research together further in this field. Thank you.
Thank you, Daniel, for this positive remark at the end. So, are there any questions from the audience?
So my active flow control device wasn't working too well. I'm getting some fatigue in my actuator down here. But no, I'm really intrigued about what your thoughts are around partnership, especially when it comes to something like a common research model. Have you given thoughts to that? And I'm thinking of like the open rotor and some of our challenges with these large turbofans.
Yes, common research models in order to have maybe also call it a public domain database for relevant geometries, for relevant maybe integration concepts. This is really maybe a next step to go. Of course, in these partnership setups, as I've shown you with these footnotes, there have been such kind of not necessarily public domain geometries, but this is definitely something to go, because it is a difficulty, of course, to share out of the OEM's perspective what really is a maybe sufficiently described next product's real arrangement in order to integrate it there. And therefore, as you say, this is maybe the step to overcome these deficiencies, where otherwise we may have principal concepts which are further maturing, but the question on how to integrate it under these realistic constraints driven from whatever, they may not be sufficiently addressed. So yes, definitely.
So yes, an excellent talk. I think you put the problem very, very nicely in a couple of presentation slides. My name is Kees van Dam. I'm UC Davis. My question, you made the example, a very good example of the engine, pylon, wing intersection there. You indicated maybe a delta CLmax of 0.1. As you would go to Airbus maybe, working on an A3XX, going to, in your conceptual design now, you could say, I can guarantee 0.1 CLmax. If I get approval, if we can put this AFC in this area. Any idea what answer you might get?
The answer probably from the chief engineer is, are you sure? Then you put your hand in the fire and you keep it there. No, the question is very valid, but on which basis can you really bet the future of the company on this? And now everyone would say, oh, maybe there's another campaign, whatever this means, up to flight test required. And then you go in this vicious circle that no one really dares to put the hand in the fire there. And then the question is maybe, is the benefit, and it's maybe then not only 0.1, but maybe far more, or you can avoid the complete leading edge device and so on, then it's maybe attractive that people say, this is a contender approach. We protect the baseline, but we allow you to go this contender approach. If it's only 0.1, as a chief engineer, I would say, difficult. Maybe reserve a tab on the flap, and then you get also 0.1 in case you don't need it, because everything is going well. We simply delete it then in the running product line. But here, maybe the size of the carrot has to be extremely attractively higher in order to shift this paradigm change. no idea where this would happen, and therefore looking a bit maybe on different kind of applications. Perhaps this is what we need, because the orders of magnitude which we see on this kind of configurations, they're appealing, but they are not changing the world. And therefore the question is, will it be ever enough to be really convincing to future chief engineers of future products after next to go the alternative way and to take whatever kind of considerations that in case you prove that it's finally not really working, you have whatever fallback. But it is something which is not easy. Say, okay, take the AFC out and put a sled in there, because you will have designed the aircraft in a way that there is only AFCs and the integrated solution, and you not can replace it in a reasonable way with something conventional, because you have followed this complete different paradigm. So let's see. Yeah?
So thank you for your presentation. Can you comment on whether any proposals in next stages of clean aviation to progress certain areas? You build ground hardware, internal testing. Do you think there's time to do a flight test at this stage? Okay, to convince about the integration and TRL readiness?
Yeah, it's a fair point. And now you would say, okay, on all what you have shown, maybe this would be the next step. The difficulty why this was a bit now falling behind, if we would know that this is the kind of engine which we have to integrate, and you could do the trade-off in terms of no classical leading-edge device possible, or you have to put 2 meters more on landing gear, and this is maybe 5 tons of additional weight, and you cannot integrate it, then probably you could do it in a targeted way. Today, if you would offer me, oh, you have one flight test free, difficult what to do with it, because this is then maybe a kind of converged solution on which you will demonstrate. Is a large-scale demonstrator really the suitable element to do still this amount of large parametric design space exploration which we need, or do you get only one shot for the proven or for the presumed attractive solution, and then you have flown it, and then you are not really clear on what are your product needs, but you don't get another one afterwards. Either you then say, okay, I bet the future of the company on flow control because I've flown it, but if you then say, yeah, we have flown it, but you never know. This is really a tricky question. The next step is required, but I'm currently a bit hesitating whether we are there to really know what we would then put on the table for such a targeted exercise. As said before, there is lots of parametric exploration still needed. Maybe not so much even on aerodynamics, but really on how to make it happen system-wise, integration-wise, and find the trade-offs there. So really tricky question. So please don't offer millions now, because I at least wouldn't say I opt for this or for that.
I'm Pavel from the Institute of Aviation in Warsaw. This is kind of a question to all of you, maybe a little bit. It's been mentioned how long research on this has progressed and how much progress has been achieved, etc. But do you think there are any conditions under which it wouldn't be worth investing in it anymore? And if so, what those conditions might be? Basically, at which point we can say as an industry, okay, we give up.
So maybe I start, but please compliment then. Sure. Good question, because if it would have been maybe 10 years ago, I say, okay, it is sufficient to replace a good product with a better one. All fine. But as we now have to strive for maybe more radical solutions in order to trigger, I wouldn't say even necessarily then the integration of whatever kind of novel energy carrier, but simply maybe have the additional strive for another 10% of efficiency, simply to reduce the energy consumption. Are these means suddenly paying itself with a higher risk, with a higher cost, but are they buying themselves now under the changing constraints for next product and also product after next? Are they buying themselves now a different way into the product? 10 years before, maybe before we started what I've shown you, probably I would have said no. There are always comparable lower hanging fruit solutions. But now it's a question, can it, as I said here on the previous page, can it be maybe the unlocking enabler to grab something which otherwise would be locked? Different kind of wing concept, different kind of engine concept, and therefore worth further exploring. It is not a purpose on its own. AFC is a means for a certain purpose, and here really maybe the landscape on what we have to address as potential technology to really consequently integrate in the next product has to open, because otherwise the range on what you could still grab is too limited even. Please compliment from your end.
Sure. Well, one, as long as the physics is real, and we have the research to date shows the physical, that there is an effect on the flow. That if you inject momentum into it, you're changing the flow characteristics. But if you look at what we on an X65 described as the enabling feature, as the enabling technology of CFD and additive manufacturing, those are not directly related to AFC. In fact, they really were developed independently, but they enabled us to think about AFC in a different way and build it into an airplane. It's possible that that will happen again, that development of other related technologies will change the way we think about AFC or the way that we think about aircraft design in general. In particular, Daniel mentioned AI and future techniques around optimization. You could imagine further development on CFD and high-performance computing, impacting our design tools and the way that we incorporate, and ultimately the certainty with which the fidelity of the design tools and our confidence in the effects. So I don't think it will go away or that we would stop working on it unless there was another way to accomplish the means that was much easier in some way. But the way we think about AFC might change, and might change dramatically.
Martiqua, do you want to offer an answer too?
Oh.
You don't have to. I was just.
No.
So my answer is biased, obviously. Otherwise, I don't have a job anymore. But to kind of add on to this, I think we're running out of conventional solutions. Like the aerodynamics, most of the systems that you see on an aircraft, the technology is 50 plus years old, right? There's nothing new to it. So obviously we've seen a lot of presentations with other aerodynamic shapes, different configurations that are kind of showing up on the horizon. The physics are there, right? Focusing the attention from just the effect side and really focusing on the integration side and the trade study side, right, to make that compelling case. Is it an enabler? Can it enable another technology which was cascade further into, right? So a CL of 0.1 was mentioned. The waterfall effect of a CL of 0.1 can be huge on an aircraft design. So as long as since we don't really have a whole lot of other stuff to push for to drive aerodynamic efficiency, I think technologies such as active flow control will become more relevant, and I hope the comfort level, right, that chief engineer or whatever, that they recognize, hey, we've done so much work with demonstrators, integration work, and it's not rocket science, right, that we're trying to propose here. And there's many other complex systems on an aircraft that we just have to go through the same engineering rigor. That I do think that there will be a place for it. And so should we stop the research? No, that's the answer. But should we maybe refocus the research? Yes, that would be my hope to the community to refocus their efforts.